All right, here we go with part four. This is a jam-packed session. We're going to get into some details that probably you'll never have to deal with, but I want to give everybody appreciation for the elements of what goes into a safety function. That's really what we're going to get into today. You've got some handouts from the previous session that you can continue to use. I know Mike is going to send out PDFs of these slides later, so you don't have to scramble so much, taking notes and stuff. You'll have some to reference. I mentioned this this notes page in here too, with this equation, dissatisfaction plus a vision plus steps to get there to overcome the resistance to change. So there may be some ideas and some things that come about as we're presenting in here that fit into one of those columns in your own scenarios there, where you're dissatisfied or what kind of visions come to mind, what goals you have, and even areas of resistance to change. So this is all also, this content is summarized in, is probably concise of a document as some of this could get, but it's about an 11-page document you'll have here titled Goals and Business Outcomes of an Investment in Machine Safety Solutions. So a long title, but this is long of a topic here too. So today, part 4 out of 5, we're going to discuss the minor surfacing exception. Last session, I teased you quite a bit about it, but it's the vital aspect of how companies can attain that aspects of not sacrificing safety or productivity. You want to gain both. Then we have one more session after that. Next week, we'll talk about what do you do with all these systems that you put in? How do you manage them going from there? So today, with no further ado, we're going to get deep into the minor surfacing exception and then the engineering controls that go with that when you're doing something other than lockout, tagout, and machine guarding. So mentioned in the first session how these best-in-class companies attain these excellent performance KPIs associated with productivity, OEE, and their injury rates, how simultaneously you can attain both. Namely, the best-in-class companies are both safe and productive. The safest companies in the world are the most productive. And this is that epiphany, a moment, when people realize, boy, you can have both. And just to mention too that correlation it's a positive correlation and scaled all the way down this report. So the safest companies in the world are most productive as well. Average in safety, average in productivity, laggards in safety, laggards in productivity as well. Now this is obviously a correlation aspect of it. Now the interesting part of it here is what we'll get into in some of these solutions. How do those best-in-class companies attain these performances as well? Well, the first is they follow these procedures that are laid out in the consensus standards, global standards that define the process at which we can attain that productivity gain as well as safety gain. And so today we're going to talk about the design and the verification of those solutions. We started getting into the solutions in step 1 in the risk assessment when we got into the existing measures and the future measures of how we're going to reduce risk. We sort of hinted into, in a general sense, here are the solutions that we're going to use to mitigate risk to an acceptable level. As we saw from the risk assessment, the standards provide some guidance as to which types of solutions and risk reduction measures that we can take based on the risk level that we see out of the risk assessment. When we did our team-based risk assessment and we got these scoring levels, this chart here out of the RIA standard basically says if I've got very high, or medium, I'm going to have to do either eliminate the hazard, design it out, or I'm going to do some sort of engineer control in there too. And that's where we're going to get into. We're going to go into these solutions here in detail. You see all the most preferred, least preferred. This is the concept of the most preferred is our solutions that rely the least on human performance or human activities and relying on humanity to do the right thing. It sort of introduces the concept of what we term as passive and active methods. So this is where we're going to talk about passive methods versus the active methods we covered before in this realm of safety. This is similar to seatbelts, is like lockout, tag out. It takes a human to actually do that, click it or tick it, So anyway, seatbelts and airbags in this case are just as effective, but one relies on a human performing versus the machine performing here automatically, as in the case with airbags. So what we're going to talk about basically is, I'll say, airbags for machinery, things where the machine does the thinking and automatically responds to a scenario to reduce risk. The other part of it, important to note too, that when we talk about these solutions, we're typically talking about the primary means of risk reduction, but that by no means limits you to just that one, quote, silver bullet. There's no silver bullet, but we'll use layers of protection to reduce risk. Typically, we're addressing probability, somewhat severity, but in the terms of risk, we're probably trying to reduce probability of an incident more than anything when we start talking about these controls. And these are also in the context of the primary means of what we're talking about, nestled between lockout, tagout, and machine guarding. This is the exception. Minor servicing exception comes into play here. So we talked earlier, the default from OSHA, they expect when we're accessing a machine, we are going to turn it off. We're going to lock out, tag out. That is a default. The other default is if the machine is running and we have hazards on it, that we put guards into it, fixed guards, and we keep people away. The realization came about that wasn't all together as safe as possible, because what we ended up, if we implement lockout, tagout, and guarding to the nth degree, we end up with a machine that looks something like this. It's somewhat inoperable, and it doesn't take into the realities that people do need to have access to these machines to run them. So the rules came about. There was an exception to the rules, and this is what we term the minor servicing exception. That had some specific requirements to say, okay, here's where we need to get it. And the phrase that we hope you memorize here when you're thinking about when somebody says, hey, we're going to allow access in here. First, have to go through this justification part of it. Routine, repetitive, and integral to the operation of the machine. That's a term I want everybody to sort of memorize. Routine, repetitive, and integral to the operation of the machine. Those are the criteria for lockout, tagout. Where it fits into the laws, into Code of Federal Regulation 29, part 1910, is primarily in the environmental controls, where lockout, tagout resides in .147 in here. And basically it's a minor clause. I mean, it's just, you see like the A2B, it's a little paragraph that basically lays out this routine, repetitive, and integral to the operation machine. But it also includes that these tasks must be performed during normal operation. And lastly, it shall be justified, and primarily with the team-based risk assessment is how that will be done. So we'll get into that in a bit. OSHA is very careful to, when they're examining a situation or a scenario, an application where a company has declared, I'm going to use a minor servicing exception. They provide some guidance in here and some pretty good training. If you go to the OSHA website, you can follow the link here when you get these slides in here, but you can find some scenarios and case studies where they determined, where lockout, tagout was required or the minor servicing exception was acceptable. So, some of them are surprising. You read through the scenarios and you go like, oh, okay, well, that seems like that should be a minor servicing exception. And then you read the outcome of the case and you go like, well, no, I can see why, and here's the reason for it. So it gives you a better understanding of the whole thing as well. When we turn to the standards, because that paragraph and even the guidance from OSHA isn't all that detailed. There is some detailed guidance out of the consensus lockout, tagout, or control of hazardous energy specification, ANSI Z244.1. If you don't have that one, this is the one you probably should have in your library, that defines lockout tagout, but it also defines alternative means. The most recent update to that one, 2016, really had quite a focus on alternative measures because lockout tagout was being, not used, as well as it should be. And boy, if there was some other means to keep the machine running better, that was really the focus, these alternative measures. So when we get into the justification part of it, if we're going to follow this flow chart in here, if we believe that the task from our risk assessment, if this task does require a person to access the machine while energy is still available, we want to try to declare, I'm going to take minor servicing to do that. We have to document that decision. We can't just do it and try to remember what the decision was. If somebody does call you up, or if there's an incident associated with it, you're going to want to have some sort of record of the thought process that one went through and the decisions were made. Ultimately, the phrase that you probably want to remember is, and the goal here is to make the best decision possible with the information available at that time. This is a type of form where you can document that and call that up later if it comes in very handy later. If you have an incident, you can review all this stuff, or if people are no longer there, what was decided by those, previously, and who signed off on it too. So I covered this briefly, and I'm happy to provide a copy of this as well. This is an IMS form that is based on Annex L out of that ANSI Z244.1. Annex L does show an example of this. This is one that was created with a little more detail, a little more kind of thought through it. So you're welcome to it. If you can justify minor servicing exception, if it's justifiable and practicable. Okay, so here's the focus of today's session are these engineer controls, and we'll go through each one of these at a time. The details of these are coming about from, and this is again the library of consensus standards that I mentioned. There's a bunch of them here, but the ones that focus on these solutions are these, and probably ANSI B11.19, the most recent one, is probably the most important one to define that. Now, it does punch out to or reference other standards that are out there, and the other one, when we're getting get into control systems, be it electric, hydraulic, pneumatic, we're going to be going to ISO 13849-1. Lastly, we can't forget the fluid power aspects of it as well, and the guarding of it. So physical guarding, movable guards, the hydraulics and pneumatics standards. So we reference all of these, out of these, well over 1,000 pages of here, roughly maybe 800 pages are associated with the solutions and the details of them as well. So we'll use the standards. And from that, also step 2, as we covered earlier, the SFRS, the Safety Functional Requirement Specification, would then provide some details on the safety function or the scenario, how the approach, if you will, defining the approach in detail, including the circuit performance that we're going to use, and as well as how we're going to diagnose that circuit and make sure that circuit performs properly. And when we refer to the circuit, a lot of times we refer to this as the safety function, and that's an aspect of functional safety. Sorry for the confusion, term in here, but basically here's the definition of a safety function. It's basically the part of the control system that's safety rated. So we're a safety rated part of the control system, the functionality of which is basically if it malfunctions, risk would increase. Okay, so that's sort of a roundabout definition of it, but it's essentially the circuits, the components, the design of it. If it's a relay, it's hardwired aspects of it, the wiring of it. If it's a programmable controller or configurable relay, it's the software that's in there as well, relying on that as well. And not just the control circuit itself, but the actuators and the physical guarding. So this would be sort of a better definition of or a look to it of what a safety function is. And the safety function becomes an entity in and of itself. And when we talk about the performance of a safety function, we're talking about the performance of the entire element. This becomes one specific element, not just the performance of each individual item in here, but this all becomes sort of the system. So this could be a valve as well, pneumatic or hydraulic valve versus a motor. This would be valves here. So, or pneumatic actuators and hydraulic actuators. When we look at the control system, today, a lot of these safety functions are integrated into the standard control system as well. So we'll have a safety rated PLC. We could have a safety relay bolted on or connected to interface wired to a standard PLC where the safety elements, the safety functions are operated by this relay. But a lot of times today, if it's a new system or if it's a retrofit or something, a lot of times a safety rated PLC will be installed in there. And when we talk about the different or the way that whole control system is made up, it's sort of a series of safety functions. So these are the elements that would be defined. These are the elements in which we're talking about the engineer control systems and control solutions, risk reduction measures. These safety functions are what we're talking about. So when it comes to machine safety, typically what we're talking about is coming to a stop or a cessation of machine motion, okay, in some form or another. And we talked a little bit about stop categories, the types of stops that are out there, a normal stop, an emergency stop. The engineer controls are where we're getting into this, what's called a protective stop or a safety stop, okay? And there's rules associated with, how I can come to a stop in here and what type of stop we're going to actually get into. So, or a category of stop. So as we mentioned before, there's a category 0 stop, a 1 and a 2. We'll talk a little bit more about these later. But then, so before we get into those engineer controls, before we get into the designing of it, we also have to consider what exactly we're going to stop. What portion of the machine are we going to stop? So it could be a portion of the machine. It could also be a portion of the line itself. So there's a sort of a layout analysis that will be done. What will these safety functions be affecting on the machine? So for instance, I could have maybe a safety function that stops one part of the machine, but I let another part of the machine still operate. If I can follow all the rules about access and proximity of where a person might be with this motion the hazards, maybe I can let the robot over here do something over here while I'm accessing over here. So you get these aspects of span of control that we're talking about. When it comes to an entire production line, you'll have the same sort of concept. If I'm going to do protective stops for this area here, maybe I can let this area over here continue to operate. And this is how sort of the magic happens of how those companies out there outperform other companies with higher OEE. Their machines aren't totally shut down, the whole thing. They'll zone them and keep parts of them running with the intent of improving the productivity aspects of it as well. So there's some details you'll get into, sort of a layout analysis of sort of the overlay like you just saw, and then you'll see some of the functional aspects of it, where different components, different elements of the machine. So all of this would be taken into consideration when we begin to design a control system that I'll want to keep some things running and some things not. Okay, so all of that context before we get into, hey, let's throw this solution out here, or hey, I think a light curtain is great. All of that has to be done ahead of time, including the risk assessment, functional requirement specifications. All these are the considerations before we get into, hey, let's throw a light curtain on there, okay, which we still hear today. I had an executive just the other day saying, why can't you just put a light curtain on it? So all right, here's kind of why you can't. Okay, you got to do all that ahead of time and take some thoughts into it. Okay, so let's get into these alternative methods. We're going to go down this list here: detect and access control. These are probably the most common ones that everybody is, here's our light curtain. Okay, so all of that consideration and where light curtains are going. So there's two types of when we do detect and access control. We'll do these terms called interlocking or guard locking. Okay. Interlocking means when I trigger the safety function. So let's say I breach this detection device, that triggers the safety function to put the machine into a safe state. Okay. Guard locking is typically something associated with a perimeter guard and a movable guard where I am interlocked with the control system, but guard locking is going to be, I'm going to hold this door closed until I reach a safe state internal. So I may trigger the safety function with an access request push button. So I say, hey, I want to get in here. I push a button on that gate. Now the PLC says, well, I'm gonna try to attain safe state. It could be stopped, it could be going slow, whatever is deemed an acceptable safe state in here. But I'm gonna hold this door shut until the machine speeds down or goes into the proper direction or whatever until I attain safe state. And then I'll actuate a solenoid on the gate or a magnet or something that will allow that gate to open. So that would be considered access control. Okay, so I'm detecting or keeping people out of there basically until I retain safe state. The standards associated with that get into some very detail about how I go about doing that. Here are some other suggestions of the library of standards that you'll need in here as well, detailing some of the ways to achieve safe state with these detection and interlock devices as well. So the detecting process, these used to be considered or talked about as safeguarding or non-separating safeguards. Is basically the term you may have heard, and a lot of people still use those. Non-separating is kind of self-explanatory. I don't have any physical barrier to the hazards in here. I'm just going to simply detect it. So there's nothing keeping me from jumping through there other than the detection by the light curtain. So those, used to be called non-separating safeguards. So the terms were changed because the word guarding in here, the latest revisions of especially the ANSI B11 standards, whenever there's a mention of the word guarding, they were actually wanted to just reference a physical guard, a fence or a gate or something that was termed and now referring to these as separating guards. So, and those separating guards can be typically movable guards as well. A movable guard is a gate, if you will. So just another means of talking about a gate. But these gates have to also, and this guarding follows the same rules and guidance as all the fixed guarding stuff that we found when we were in this standard here, the design and construction of fixed and movable guards from ISO 14120 will define all of that stuff. And the term you may want to, if you're evaluating a guard in there, try to remember this acronym here is the auto test is around, under, through. Can I access, around, under, and through this guard? If you can reach the hazard, then you probably have failed a guarding evaluation and there needs to be rethought. But that also, basically when I'm doing a movable guard, I'm going through that guard somewhere. It's a breach of the perimeter guard with a movable guard. I'm going to go through it. I still need to follow the same rules in terms of can I reach the hazard. So you'll see these things called gotcha sticks that follow some of the physiology of basic human hands and arms and lengths and stuff like that. You first test that, but then the other thing that we'll need to test as well is make sure, and this is something that will come out of the functional requirement specification, is how fast do I need to attain a safe state? And basically looking at the application, what is the safe distance that my guards have to be from the hazard? So in this case, the example here would be a detection device. When I breach this light curtain, how fast does this machine have to come to, let's say, a stop? Fully stopped is a safe state. How fast do I need to get to that? So this used to be a stop time calculation, but sometimes we're not stopping. You'll see later with a category 2 stop, we may just be slowing down, but it basically, how soon do I need to attain safe state? So a safety distance calculation would determine how far from the hazard does this, based on how fast the machine can come to a stop. I may have to put this light curtain, 2, 3, 4, 5, 8 feet back based on how fast a human can breach that and get to the standard. So that study following these calculations would have to be made. And the same would go for if I'm using a separating guard and a movable guard. When I say I interlock that with the control system, when I open that door and I trigger the safety function, how much time do I have for that machine to come to a safe state? So this would also determine that how far does this physical guard need to be from the hazard as well. So it's the same safety distance calculation. Okay, so that was a quick run through of detect and access control. Let's take a look at control of hazardous motion. This is another really cool one where we're going to get into some pretty neat technology here as well. The first one is most typically used as two-hand single actuation type of. You've seen those out there, two-hand controls. This was an alternative to what's called the pullback. Typically don't, those are very rare today. If you remember the straps that would be on somebody's wrist, and there would be some device that would hold or pull back somebody's hands from, say, a press. Those are still in the standards, but they're rarely used. Today, there's typically a combination of a two-hand control and, as you can see in here, a light curtain. So some means of keeping or repositioning the operator someplace as well. Now, these buttons can be somewhere, maybe somewhere else on the machine. It doesn't necessarily have to be like right there where the point of operation is, but it could be, somewhere where I need to make sure the machine operator walks over to this position and pushes those buttons and stays clear of it. Okay, so two-hand palm buttons and whatnot are means of doing that too. And the single action means that these buttons have to be pressed simultaneously to show that, okay, both hands, I can't push one or put a broom or a weight on one of them and push another one. So the control system would allow that anti-tie down sort of circuitry and magic would go on in there to ensure that, okay, there's no other way to do it other than two hands pushing it. The other one in here that's very common in here is today they're called enabling devices. Enable switch in here. They used to be called the dead man switch. So this would be something that I would allow a person to access a hazardous area, but only in certain conditions. And this would be something that would allow them to immediately turn the thing off or go to maybe a totally safe state versus an acceptable safe state. So let's say I'm in a threading operation where I need to thread a coil into, through a bunch of rolls. I might use, some slow speed and allow the person that in there, through the gate. I've opened the gate. I'm in this sort of safe state, which is kind of slow. But the person's going to hold on to this thing. And the newer ones today, and if you have some that are still two position, consider going to a 3-position switch on here where the center is on. And the reason for that, the change to the standard was made and the recommendations for the center on position is that in some cases, when somebody was injured, instead of them dropping or opening, typically it was, you squeeze this thing in. As long as somebody's squeezing it, it meant that you could still run. So it was a 2-position, the person squeezing it puts it in the safe position too. But what was found was that when people get injured, they didn't necessarily open their hand, they clenched it tight. So the 3rd position was added. So with a pod, the center would be the enabling position. If somebody got hurt, they could either squeeze it or drop it, and that would, put it basically into a safe state. Okay, so the term dead man switch also isn't, gender neutral either. The term came from the railroad industry to prevent runaway trains, where the engineer, in the locomotive would stand on this switch, and if he ever fell off of it or died and keeled over, hopefully they fall off the switch. the train would come to a stop. So that's where those things were embedded and brought into machinery from there. Okay, next one is restricting operations. This is essentially the concept of forcing the following of a proper procedure. And probably the most common way of doing that is what's called a Trapkey system. I'm going to use some interlocking guards and stuff like that. And the access is supposed to be, look, I'm going to allow that person access, but I want to make sure that they're into a safe state and always remain in a safe state when access has been granted. So the Trapkey Systems has been recently really focused on and enhanced as a pretty effective way to ensure that people follow the right procedures. So an example of this, I've got a couple of pictures here, some real applications here that this is a machine here that this whole gantry moves back and forth and up and down, and there's some plastic rolls that spin on this track here, and you end up with a coil on these rolls here that gets wrapped into plastic. You might have seen those on, on the highway if you're not working in the metals industry. How do those coils get wrapped up? And this is the type of machine it used. So it's a fairly dangerous machine. There's a lot of hazardous motion. This thing moves pretty fast. It's all automated. It'll move at a random up and down and back and forth and in and out. Really no means of detecting a human in there. If somebody's in there and this machine's going through its sequence, it's going to continue to go through its sequence regardless of what happens to the human. So the other thing that happens are sometimes these coils don't get seated properly on these rolls, and they walk off and go smashing through the floor or smash, right on top of somebody. So anyway, so this company wanted to ensure that there was nobody inside this perimeter. So the first solution is to put perimeter guarding that was at a proper height, so somebody couldn't get into there other than through specific access gates. And then they have these access gates interlocked. So the scenario to allow this person to enter this hazardous areas, we want to make sure everything is turned off. There's no motion in here at all. So the sequence you kind of see laid out here is that there's a key switch that is interlocked with the control system that's managing and controlling all of the motion that's in here. So the operator would turn this switch here, and that would release what's called an access key. And then we would bring that access key, we'll go over here, take this key out of this panel in here, and they would walk over to this gate, insert that access key into the gate, turn it, and then that unlocks a separate key called the safety key. That now they can turn that safety key, extract it. Now the gate is open. Before it was interlocked and you couldn't get in it, but the only way to get into it is to remove that safety key. The only way you can remove the safety key is to get the access key out of the control panel. The only way you can get it out of the control panel is to put the machine into safe state by switching it. There's no way to defeat all that. So I'll get back to the gate now opens, and that he can take that safety key in here, and now he can actually insert that safety key into the control panel here and enable this control panel here. This control panel has been disabled, and it'll allow him to operate and manipulate this machine in here. And then the only way to get the machine back into its normal operation is to reverse that whole sequence. So that's basically it. It's a trap key. It's referred to also captive key, but it ensures that somebody follows the proper procedure. And all of that is interlocked with a safety rated control system with these access gates. So it's a pretty cool way to do that. Okay, so next one is where we're going to monitor or limit the hazard. A lot of times this is some of the things that we're going to talk about that really lend to increases of productivity. And now we're going to come back and we're going to visit the types of stops that we're going to get to. This is the goal. This would be what would be determined by the risk assessment and functional requirements spec. Do I need to come to a category? Is a category 0 stop, sufficient? Category 0 stop or category 1 stop? Both of those are possible with a thing called safe torque off. It's probably the most common way of using kind of this magic in here. But you can have two types of stops with safe torque off. One is that I immediately isolate the power, and I'm going to use the drive or a valve. I'm going to use those safety rated elements to isolate the energy going to the actuator, the motor, or the hydraulic or pneumatic actuator. So that's a way to attain a safe state very quickly, but I'm not going to turn off power to the whole machine. I'm not going to lock out, right? There's still energy available. And the important part of that is one, attaining a safe state, attaining, the safe, state of where energy is flowing to actuators. But more importantly is what does it take to get back to normal operations once I'm done with the task internally. So we'll talk about category 0, 1 here. These are the examples of it. And by these diagrams in here, you see velocity and time. In this category 0, you can see I'm going to totally isolate energy instantly, boom, and I'm probably going to coast to the stop. What brings it to the stop are the effects of the machine, be it friction or inertia, will bring that machine to a stop. Sometimes that's acceptable. Sometimes I want to bring it to a faster stop, so I'm going to have to keep the drive and motor operating, where I'm going to power this thing down faster than if it would coast if I had an higher inertial load, or if a high friction load would, say, upset the mechanics, maybe things would topple over. If I stop something, I want to ramp this down. I want to take it to a controlled stop and then isolate it. The drive is still available. The energy to the drive is there, but the drive is isolating the energy to the actuator or motor. Same thing can be happening with a pneumatic valve, hydraulic, or a safety rated valve to the hydraulic or pneumatic actuator. So, and those would be triggered, with a switch. So basically, these are the first two elements, that are the simplest and most common ways of attaining those, and I'll say the magic of attaining the safety and productivity. But the further sophisticated means are these category 2 stops. These category 2 stops, one, obviously you can't use these for an emergency stop only, but these are going to be for the protective stops or safety stops only. So these are termed, in various means. And again, we're going to utilize this entire safety function. I'll show you some examples of this. This is probably the most common one, where I need to hold a position. Maybe there's some gravity affecting it, or some external effect on the machine, but I want to hold this thing from a safety perspective. I have to keep this machine in this particular position while somebody is making access. You'll see the velocity comes down to 0. I stop here, but I'm going to use torque to, let's say, the motor or to the valve. I'm going to keep energy available to the actuator itself, in this case a motor. I'm in a hold position, and I'm going to use the energy of it to not allow it to change position higher or lower. It's going to stay there. Okay. And this is all defined in the standards of how you go about to do this, and the technology is available. The magic comes now with that availability of energy to the actuators. There's all sorts of great things that you can do with them. And, if we had time, we would sort of get into each one of these in the workshops that we typically do, and talk about potential applications in your plant to say, wow, hey, you can do this to maybe you introduce things about not just holding position, but maybe ideas of safe direction, safe positioning, it's limited speed. Maybe I can go faster or slower, or a combination of direction and speed, the actuator. So it becomes, almost limitless, but there's some pretty cool ways you can get into getting to a safe state that may not be stopped, and it's certainly not going to take a long time to return to normal operation. So I'll show you an example here of something out of the printing industry. The task here is that the rollers on a printer get dirty quite a bit, and they require cleaning on a regular basis. So the scenario that we have here is that we've got a movable guard in here, and it's interlocked here with the control system. And the safe state in this case is that you see the green direction of these rollers. These are rolling in the opposite direction of the normal operation. Normally, this would be a very hazardous in-running nip, but I need to clean both of these rollers around all 360 degrees of it, but I can only access about maybe 20 degrees, 30 degrees of it at the most at any one time. So it'd be really nice if I could keep these rolling in a safe direction, outrunning nip, and also at a slow speed that will allow me time to wipe these down, clean them with some sort of solvent or whatever I'm going to use, get them to clean as they move while I'm in there. And you can see in this case too, I've got an enabled device. He's holding on to that in case anything ever happens. He can let go or squeeze it and would come to a stop. But the safety function, the architecture that the control architecture that would be used in this case would be some sort of positioning and speed sensing, the enabled device, and then the interlock you see on here, all going into a safety rated PLC, and then we use a safety rated drive to then utilize these functions of the safe torque off, and then the speed range, the safe speed in here, and then also the safe direction. Okay, so the alternative to that is lockout tagout. I'm going to go through a very cumbersome, very time-consuming aspect of shutting it down and turning back on just so I can increment it to get to, each of the 30-degree segments of each of those rollers. You can imagine, it could take half an hour to clean all those rolls, whereas in a case like this, you could reduce it down to maybe 2 or 3 minutes. And then as soon as I step out of there, I close this gate and I ensure nobody's in there. I return to operation immediately. Okay. So this is some of the magic of how do those companies attain I'll say the causation part of it. When we study these best-in-class companies, they're utilizing this advanced technology. They've got policies and procedures and standards in which they apply all of these things as well. But they also have a culture that says, hey, I deem safety as a productivity gain. I want to attain both. So that's how some of the ideas of how they go do that. So we're relying on a circuit, components, the components, the wiring, the software, the firmware in there. Now we're going, okay, one of the elements of minor servicing exception is that whatever I do, besides lockout tagout, I cannot increase the risk to the person gaining access in it. So I've got to make sure that this circuit is really good and that it won't fail. Okay. Now I've detailed that the circuit performance in my safety functional requirement specification. It came from this whole process of the risk assessment. So you can see how this whole safety life cycle, ties into each other. Associated with our sessions here, we talked about in session 1, do I have the culture, do I have the policies and procedures to follow all of this, and do I utilize technology as well, the safety maturity aspects of it, and that we talked about in session 1. But you can see how all of this sort of fits together into the context. But here's where it comes down to deciding what the control engineer is actually going to design, is based on all of that proceeding when it gets down to actually picking out components and putting a wiring diagram together. So in this case here, in order to properly design something, we need to know what the level of risk is that we're protecting against. And then we're going to get into something here where we're going to go into this ISO 13849-1, the performance levels. And that's when we're finally getting into this portion of it around the safety life cycle. I'm going to now be able to design these safety circuits. So the performance levels are, I'll say, somewhat of a rival or a counterpart to SIL, safety integrity levels. Safety integrity levels comes out of a different standard. It's an IEC 62061 standard. The problem, or I guess the reason we don't use that in machine safety as much is that it only the SIL ratings and stuff are only applicable to electrical and electronic components. If we're using hydraulics or pneumatics as actuators, it doesn't apply. There's no means of it. So, but ISO 13849 covers hydraulics and pneumatics as well as the electrical and electronics of it, and it gets a little more detailed in terms of the standard of, or the design criteria that it takes. So if you're in a company and you hear people talking about the SIL rating, and we're talking about machines versus process control, where we're talking about a continuous like batch process or something, that's where SIL has migrated to. So we still use SIL because there's still electronics doing process control and process safety, It's typically only going to be electrical electronics systems, whereas in machine safety, we're using hydraulics, pneumatics, and electric systems. So you have to use 13849 to address all of that. So that is a standard, another one that should be in your library if you are going to go about designing these. Because if we do use the fluid powers, they're going to reference 13849. If we do any of the previous systems, ANSI B11, NFPA 79, all of them will point to details in 13849. So that is the consummate one. And that's where we're going to get into some of these designs of the safety functions of it. So basically what we're going to talk about here, and when we mean how good is this, this circuit, we're going to refer to it as performance levels, okay? And what we're talking about, the performance level of the entire system here, the gate, the switch, the wiring of the switch to the safety logic device, a relay or a PLC, and then how is that wired to the actuator controls, units here, the driver, contactor, the design of the circuit, and even the elements out here. So here it is. Here's performance level A through B. So or A through E. Basically, essentially what the performance level is going to dictate, and we'll get into each one of these attributes, and this you'll understand a little more about this chart in a moment. But basically what we're trying to get down to here is the determination of how good that circuit is in terms of, can it fail? And any of them can fail to a dangerous state. So we want to define the probability of that happening. So you'll see the levels of probability here. It's the probability of failure per hour to a dangerous state. That's what you'll see this acronym here. But basically it's saying if I've got a performance level A here, on any given time within the mission of the machine system, or the mission of the safety function, that I've got a 1 in 10,000 chance that a circuit designed to performance level A is going to fail to a dangerous state. Meaning every hour, if I could access that, 10,000 times on average, at some point, there could be a failure, 1 in 10,000. And you can see it increments all the way up to here. So when I relate these to the risk level, when we have permanent damage, amputations or death here, we're going to want to get into the performance or the probability levels of 1 in a million or 1 in 10 million that is going to fail to a dangerous state. So meaning, I can pretty well trust it. Okay. So let's get into the elements of how do we determine this? And this is what a control engineer, if we're going to use minor servicing and we're saying, hey, put a light current in here, it's going to say, well, how do you want me to design the circuit? Here are the attributes that would go into the circuit design. And there are 4 of them here. The wiring structure, we'll get into aspects of this. I'll show you with monitoring and diagnostics and duality or redundancy of it. And then the quality of it. When will those components wear out? How reliable are they and for how long? At some point, everything breaks. Everything does have a life. If it does fail to an unsafe state, can I detect it? Is the test quality of it? And then how in the scenario in which this circuit is going to be applied in here, what kind of common cause failure or common cause things could make that thing fail? Okay, so those are the 4 components of it. When I look at the structure, we pulled structure from a previous standard, EN 954. That was a European norm that goes way back, and that was withdrawn in 2008 when 13849 was put into place. But it retained these aspects of categories, so you'll still see, say, PLD category 3. That's what these are referring to. Basically, what it is basically the 3 elements: input, logic, output devices. How are they wired? Are there dual channel? Are there 2 wires versus 1 wire? And also internally, are they monitoring it themselves internally, or are they monitoring it themselves externally as well? So you'll see some duality and aspects of monitoring. The next element of it is trying to determine at what point will these things fail or have a higher probability of failing, where they become less reliable. I don't want to rely on it. So there'll be some calculations based on and mostly determine how many times will these things be actuated in a year period. And you'll end up getting through these calculations how many years we can expect this thing to be as reliable as we would want it to be, to allow, or say, my daughter to reach her arm through that light curtain and the machine won't fail to an unsafe state and chop her arm off. The scenario in here, it's saying basically it'll go almost 29 years before I've got to worry about it based on how many times I'm going to operate that. So the key is, though, knowing and assuming how many times you're going to operate it versus the reality of it. We'll talk about that in session 5 to ensure that we're actually using the machine like we said we were. So you go through these calculations, and in the case here, we said almost 29 years in here, so that would give us we almost hit the high, but we've got a medium. So that would go into our calculation as well. And you'll see all these lay out on the chart when we get to after these. So the diagnostic coverage, this is sort of the tree. We know this thing is going to fail, and if it fails to a safe state, great. If it fails to a dangerous state, the question is, can we detect that? So I could have failures. If it fails, it may fail to a safe state, it may just turn off, fault, or it may fail to a place where it's still running. If it's still running, can I detect that? So there's another sort of scale on that of how much coverage can I have, basically what percentage of it can I detect an unsafe failure. So you can see in the high here, I'm going to see 99% or more of the dangerous failures I'm going to be able to detect. So medium, you can see 90%, and low would be 60%. Okay, so your control engineer would have to put all those elements, the input device, logic device, each safety function, go through this calculation, based on the information about, from the manufacturers of how well I can see this stuff. And in this case, in the scenario, if we did a workshop here, we would go through some workshop or some scenarios here. In this case, through this calculation, you can see I would come to about 96.7% of the time I'm going to be able to see a dangerous failure. That would put me on the medium size here as well. Okay, so that would be step 3. The fourth element here is common cause failure. So things like that are how hot does a control cabinet get, or could it get doused with water? Something that could affect, we'll say, both channels of a control system, or both channels of the wiring. Something that would affect common elements of that control system, some sort of external influence on it, including, competency as well as how well, we've got trained people on how to own a control system like that. Okay, so that was a quick run through. Obviously, I just wanted to give you an idea of what goes into designing a control circuit. When you have somebody say, hey, let's put a light curtain in here. Okay, you're going to put a light curtain in here. That's the input device of this whole safety function. We're going to have to calculate all of this stuff. That's what a safety automation engineer would go through. These are and that's why you might see a bill for that kind of engineering. But again, we're relying on this control circuit to allow access to that machine. So if this was my daughter reaching into that system, and I'm relying on a control system, to do that, I would want probably a PLE rated solution in here, that knowing that could kill her. The only thing keeping me from doing that and keeping that scenario from happening is this control circuit. I'd certainly want to go through that whole process as well. So that's just a real quick overview. I just wanted to give everybody just an appreciation for what goes into a control circuit. So those are the pieces of it. You may hear OSHA talk about something. They typically don't talk about performance levels or SIL. They'll want to see a binary thing, a go, no go thing called control reliability. Control reliability is defined basically that it says that one fault in the control system, the safety rated part of the control system, will not increase risk. So in other words, it can tolerate one short circuit or one broken wire. control reliability's limit is that it can only do one fault. If there are two broken wires or two wires shorted in here, that's not that would require something a little bit higher than something called control reliability. Okay, so if you got questions on that, this is a defined in various ways, but in terms of 13849, it's something that you would say if you've got a performance level D category 3 solution out there, and you can prove that to OSHA, then they'll say, okay, that's control reliable. One fault will not reduce a hazard. Okay, so another thing too, if we had some time as well, we would go through. I've got a colleague that did some really cool PowerPoint animation that will go through the internals of safety circuits, and we'll actually see an animated version of this, of what it would take to bring that machine to a safe state. Okay, so step 3 is made up of 2 parts. Let's say we've got the design done here, but now we want to have a third-party verification of that. The third-party verification is done by something called Systema. It's an acronym for basically a piece of software that's produced in Europe that would verify that all of those calculations that I did for the structure, the reliability, the diagnostics, where do I actually fall? I think as I did them by hand, as I picked out all the components and I designed my wiring circuit, I'll basically put those into this software in various measures. So I'll sort of break these down into components and load each one of these elements or blocks into Systema, and it will perform basically a calculation. And there's links to databases that are provided by manufacturers of safety rated products like relays and drives and valves to determine the reliability of it. They've done testing on those. When will those things actually fail? They ran them tens of millions of times. When did they stop working, or when did a significant batch of them fail? So anyway, this is an automated way. So in case your engineer is going like, holy crap, I'm never going to do all that manual calculation, there is a somewhat simpler way and more effective way is the software. It's free, you download it, but it's not for the faint of heart. It's for safety professional to use. If you download it without any sort of understanding of it, it's probably tough to use. But you're going to end up with a document, and that's probably one of the most important elements of it when we come into aspects of safety. Can I document and prove that my design was good and it is properly verified? Okay, so that takes us up to the end of today's content. Here I've designed, I've verified, and next we'll talk about the installation of these control systems, and most importantly, the validation and testing of them once they're installed. And then once after they're installed and running, how do I monitor those? We'll cover that in session 5 next Wednesday, the post-commissioning and management of change aspect of these circuits and these solutions that I'm relying on to prevent my daughter's arm from getting cut off when she reaches into that machine. Okay, so that is a quick whirlwind of probably 3 or 4 hours of the workshop jammed into an hour. So I did this mostly really to give safety professionals an understanding and appreciation for what a control engineer must do to allow your company to be compliant with the standards and the laws. That's it, Mike. Hope that and Nick, hope that covered things and wasn't too fast or confusing, but certainly I'm happy to expound on any of that further either in this session here. I know we're out of time, but just send me an email, phone calls, or whatever. But if you got time right now, we can certainly cover whatever questions might have popped up here. I can't hear you, Nick. You might be muted.
I didn't see any specific comments pop up during the presentation today, but that was a lot of information for us to digest in a short amount of time. You always do an amazing job with that. We are thankful for that. I encourage our members to take a look at this, digest this, think about how you can apply it, and what specific areas you may struggle with in your organization. And reach out to myself or Mark, and we'll help direct you on the right path to get you going in the right way. I often see the minor servicing exception abused and used in the wrong ways. So understanding that and doing this properly is going to help keep your workers safe.
Yep.
Mark, thanks again. Great information. If there's any questions, if you guys are still on there, go ahead and type in the chat. Mark said he has a few more minutes. Get in. If not, we'll go ahead and shut this down. All right, Mark. Well, it looks like we don't have any questions, and we'll be emailing out that slides once you get them to me, and we'll send everyone a link to the videos. And we made them all public now, so you don't have to be a member. The way everyone could access them and get the information out there. So for everyone left, thank you for staying with us. And Mark, amazing job again. Can't toot your horn
Thanks.
enough. Thank you.
We got one more next week. Hope to see you guys next week.
We'll be there.